We're now going to learn about the Blasius relations. These relations are equations that relate the force and moment to the complex velocity potential or complex velocity. So we're gonna show them in terms of the complex velocity, and these were published in 1908 by Blasius, who was one of Ludwig Prandtl's early students, one of his first students. So let's start off with some closed surface again, and we've got a velocity vector field through this we call V, and we're going to integrate around in ds, and we've got a normal at each location along that surface. And so we would find that the force, if we were to integrate this, we can actually compute the force on the fluid within this region, and that force is equal to minus the integral of the pressure times the normal ds minus the integral of v rho v dot n ds. Okay, so one thing we might notice here is that this first term is an integral of the normal pressure forces. You know, as we walk around this surface here, we're integrating the normal, multiplying that by the pressure, or the local pressure, and so that will give us a net force due to a difference in pressure on this surface. Okay. Now this term here, we are looking at the momentum of the fluid. So there's a net force due to a difference in momentum as we move around this, and so we're looking at the momentum, so to speak, normal to each of these to the surface at any one location, and integrating that around, and so we'll get a difference in momentum. And both of these integrals, we actually have vectors inside of the integrands here. So we've got a v dot v or v dot n, which will be a scalar, but then that's multiplied by a vector here. And we've got a vector here. So what we get out of all of this is a total force vector on this fluid due to these integrands where we walk around the surface. Okay. So I'll just write this out here. This is basically due to the normal pressure, and this term here is due to the normal momentum. Okay, now we know that pressure can be put in terms of velocity from Bernoulli's equation. So this is from Bernoulli's, and so if we do that, then we get an equation that looks like this: F equals 1/2 rho the integral of v squared, which is a scalar, n ds, minus, and then I'm going to pull the rho out front of the second integrand because we're saying that that's constant for an incompressible flow. And we've got v dot n ds. Okay, so this is our new form of the equation, all in terms of velocity, because pressure can be related to velocity from Bernoulli's equation for an inviscid flow. Okay, so now the left-hand side, this force actually has two components to it. It's got an x component and a y component, and so I can break that up. The x component, we usually call that the axial force, so that's some force, and by the way, I've got this little tilde above it to mean a sectional property. So that's per unit span, which or per unit length in and out of the page. Okay, so we've got some axial force in the x-hat direction, plus some normal force in the y-hat direction. So up here we're going to basically divide this force into a normal force and an axial force. Okay, so now that is equal to, and I'm not going to write this whole thing out, but this velocity, this whole term here can be put in terms of a velocity in the x direction and a velocity in the y direction. We can split up the velocity into the two components. We can split up ds into the two components. We can split up the normal force into two components, just x and y, because we're just in two dimensions here. And so once you do that and work it all out, you can write this entire right-hand side as a function of the velocity in the x direction and the y direction. And once we've done that, we can actually put it in terms of some function of the complex velocity, which has both x and y built into it. And so when we do that, what we get is we get this axial force, and I'm going to write it as minus in. So we're going to put the normal force in the complex position there, axial in the real. And that is equal to I times 1/2 rho, the integral over c of the complex velocity squared dz. Okay, so this is our first relation. This tells us how the axial and normal force are related to the complex velocity over here. Remember, that's what we were trying to do. We're trying to get the force as a function of this complex velocity, which we can do once we split this velocity into its components and then write that in terms of the complex velocity. Okay, so this is pretty incredible that if we know the complex velocity as a function of z, so if we know the complex velocity at any place in this domain as a function of z, we can integrate that around this closed surface and compute the axial and normal forces on that exerted by that fluid or in that fluid domain. Okay, so let's work through this one more time. Whoops. Let me do that again. So we're going to work through this again and look at the moment. So the moment can be written as, it also depends on the pressure and the momentum around the entire surface here. But it's actually the integral of r cross pressure times n ds. So this first term here, we're actually going to cross that. If we go to any point on this surface, we're computing the moment about the origin. And so we take the distance, which we're going to call r here, and that's a vector from the origin out to that point. And we're going to cross the forces with r, and that will tell us the moment about the origin. Okay, so that's our first term from pressure, and then we've got the integral of r cross the momentum term, which is v rho v dot n ds. And because so this r is always going to lie in the xy plane here. Okay, so it only has two components. And these forces, again, this is the pressure and the momentum forces, just like we had here before. These forces also only lie in the xy plane. And so if we do r cross some vector and both of these vectors lie in the xy plane, we will always get a solution that lies, the final vector is going to be in the z direction. So it turns out that we don't get any moment in the moment about x-axis or y-axis. What we get is a moment about the z-axis. So we can work through this exactly like we did before, where we have pressure is a function of velocity. So we can swap that out from Bernoulli's equation and follow the same steps as before. And what we'll get here at the end is a moment. Let me actually move this down. So we're going to get a moment. This is a sectional moment, and I'm going to put an O there to represent about the origin, is equal to 1/2 rho times the real part of the integral of w of z squared times z dz. Okay, so before we had wz squared dz here in this integrand, and now it turns out that the moment about the origin is that same integral with just a z inside of it here. And then it's the real part of that. So that gives us our what we would call the pitching moment in this two-dimensional plane here, xy. So these equations here are what are called the Blasius relations. They tell us what the forces and moments are as a function of our complex velocity w of z. So I didn't show all the steps here, but you'd follow the same type of thing where all of these velocity components here, we just swap out for vx and vy. And when you do that, it's pretty amazing that it comes out to such a simple equation here to tell us what the forces and moments are as a function of this complex velocity.